Our mission to the International Space Station is not the only thing that NASA is doing, of course. In fact, we're now less than 1 week away from the next Mars landing. NASA's Mars Science Laboratory with the rover Curiosity is due to land on Mars early in the morning next Monday, August the 6th. You're going to be seeing more coverage of the MSL mission on NASA television as we get closer to landing. That'll include features from the Jet Propulsion Laboratory in California, which manages the mission, as well as here at the Johnson Space Center in Houston, where some of the members of the Mars Science Laboratory team are located. And one of them is here with us today to talk about the goals of that mission. Dr. Doug Archer is a fellow in NASA's postdoctoral program and a member of the Sample Analysis at Mars science team. Doug, tell me first of all, how long have you been a part of the SAM team?
Well, I've been a part of the SAM team for a little bit over 2 years now, and I got involved by working with some Mars scientists here at JSC, and knew that they were involved in MSL and came out here to JSC to work with them and to work on MSL.
This isn't even your first trip to Mars. I think that's pretty cool. You were part of a previous landing on Mars team, right?
Yeah, I had the amazing experience to work as a science team member on the 2008 Phoenix Mars Scout mission that landed on the northern plains of Mars a few years ago, and I was able to help participate in the build up to the mission and then landed ops and things like looking at sample acquisition and how to get a sample and where to dig for a sample. And we're actually still involved here at JSC in analyzing some of the data that were returned by the TIGA instrument on Phoenix, which is a mass spectrometer that has some capabilities similar to that of the SAM instrument on MSL.
Is landing on Mars all we might imagine it to be?
I got to say, it's probably one of the most exciting thing that's ever happened to me in my life. It's a nerve-wracking few minutes, but incredibly exciting.
The MSL mission has got some big goals. Can you summarize it for us? What is MSL intending to find or to learn?
Yeah, so in one word, it's habitability. MSL is trying to analyze and investigate the habitability of our landing site. And when I say habitability, I'm not talking about looking for life per se. Really, it's looking for an environment where life could survive, where life could be okay, either at some point in the past on Mars or maybe up even to today. But again, it's looking for habitability, not for life itself. And it does that by using its suite of 10 instruments, which look at things like the geology, the geochemistry, the radiation environment, and a whole host of other factors, which are really interesting in and of themselves. But together, they can paint a really complete picture of if this environment is somewhere where life as we know it could have survived in the past or possibly today.
That would lead one to think that there's something special about the landing site that you've chosen. That you think there's something there that you need to go see.
Yeah, so we're landing in a place called Gale Crater, but the first criteria for any landing site is that it has to be safe. That's the #1 priority, because it's really difficult to do science on the surface of Mars if you don't land safely. So that's your #1 priority. But it's also very interesting from a scientific perspective. Again, we're landing at the bottom of this large crater, Gale Crater. And when we land, we think we might be on top of some material that's been moved down from the crater walls. And so even though we don't really have the intention to go see the crater walls themselves because they're so far away, we might get a little glimpse of what's in them just because they're going to be there where we land.
How big a crater are we talking about?
It's about 150 kilometers or 110, 120 miles across. So this is a very large impact crater. Then after we land, as we look around, we're going to see this huge mountain that's 5 kilometers or 3 miles high in the center of the crater. And it's made up of these layers that were laid down over millions of years of Martian history. So as we move away from our landing site and we drive towards and ultimately up onto this mountain, we'll be investigating hundreds of millions of years of Martian history.
And investigating the area between the landing site and the mountain all along the way.
Yeah,
right?
we're the science team is whenever we see something interesting, it's easy to get distracted. So you see something fun, you want to go fun and different, you want to go see what it is. And one of the great things about exploring Mars or exploring anywhere really is that it is exploration, and you find something new and unexpected every time you go, and that's really part of the fun and the reward of doing this.
Because right now you don't know what you don't know.
Exactly. I mean, everybody comes up with good ideas of what you think you're going to see when you get there, but every single time we've been surprised.
Mentioned that you are part of the SAM team. Tell me about the components of that instrument and what it in particular is going to be looking for.
Yeah, so SAM the main goal is to look for organic molecules. But we're also going to be looking for inorganic molecules that could tell you something about which minerals are there. And both of those things really tell you a lot about the habitability of the site. And SAM, at its heart, is a gas analysis instrument. So the first thing that you have to do is get a sample of gas to analyze. And there's one of two ways to do that. The first and the easiest is just to open up the instrument to the atmosphere, take a sniff, measure the composition of the Martian atmosphere, and see what's there. The second is MSL can deliver a sample of rock or soil to SAM. SAM takes the sample and can heat it up to about 1,000 degrees Celsius. And as you're heating up the sample, it's giving off gas. Things like if there are organics in the sample, those will start to come off. And some minerals also will break down below 1,000 degrees. And so you can get a good idea of what's in the sample. So then you have that gas, and SAM analyzes it using one of three instruments within the instrument, which are the mass spectrometer, the gas chromatograph, and the tunable laser spectrometer. And the mass spectrometer tells you what molecules are in the gas. The gas chromatograph can be used if you have a really complicated organic signal. It can help tease apart what's there so you get a better understanding of what's in your sample.
Tease apart the
molecules?
Organics,
yeah. So if you say you have a big clump of organics that comes off at some temperature, the gas chromatograph will help to separate those based on the properties of the organics, so you can get a better idea. So it kind of slows things down, I guess, so you can get a better idea of what's there, a better understanding of what's there. And then the tunable laser spectrometer is an instrument that's looking for three things: carbon dioxide, water, and methane. And it can very sensitively measure the abundance of those three things, and it also measures the isotopes of those different molecules. And that's really important because, for example, with water, if you measure the isotopic ratio of water, deuterium, and hydrogen in the atmosphere, that it can actually tell you something about the history of water throughout on Mars, throughout the history of Mars.
Not just in that location on Mars.
Yeah, because you're looking at the atmosphere, and the atmosphere is, pretty well mixed. It can tell you something about Mars as a whole over very long time periods.
You help clarify for those of us who did really poorly in science. When you talk about organic molecules, are you talking about molecules from things that are alive or once were alive?
Yeah, so again, MSL is in a life detection mission, so it's not going to be able to answer the question about whether these things were ever alive or not. But organic molecules are the chemical building blocks of life. They're things like amino acids and sugars, things that are absolutely necessary to life as we know it. However, there are also non-biological processes that can produce these organic molecules. So just because you detect an organic molecule, that doesn't mean that there was necessarily life. So what MSL is going to do, again, is detecting these organics, we can say, that's a habitable environment. And that's going to help us to know where to look for life in the future.
Habitable, whether or not it was habitated.
Right, inhabited, yes.
Thank you very much.
Yes.
We often talk about life as we know it. Is it possible that there is life there, but it is so different than what we know that we don't recognize the evidence of it?
Yeah, so this is something that comes up in the astrobiology community all the time. How do you look for something that you don't know what you're looking for? So the approach that we take is say, right now it's hard enough to detect life as we know it. Let's start there. But certainly it's possible that Mars or life could surprise us, and we're always open to that possibility. But we'll see what Mars gives us.
The notes indicate that the SAM work, some of that work that's being done here in Houston, has to do with volatile-bearing minerals. Tell me what those are. What would that tell you if you found that?
So a volatile-bearing mineral is something like a carbonate or a sulfate or a phyllosilicate or a clay. And those are important because they're minerals that are produced when other rocks or minerals are broken down, and they generally imply the presence of water. So carbonate, for example, will form when you have carbon dioxide reacting with atoms of calcium or magnesium, for example, from another rock, and again, it implies the presence of water. And it requires a certain water chemistry. So that's important because just by looking at a rock, if you detect a carbonate, you can say something about how much water was there when it formed, what the chemistry of that water might have been. It tells you something about how much CO2 might have been in the atmosphere, which has important implications for climate. So you can learn all of those things about the history of that rock, or the history of the site, just by looking at a rock. It's pretty incredible.
And Sam has the instruments that is
Yeah,
able to do all of those things.
Yes, in concert with other instruments on MSL. It really is an integrated science package or science payload that by themselves the instruments are pretty incredible, but together you can tell a very complete story of the landing site.
I mentioned earlier that this mission is managed at the Jet Propulsion Laboratory. Are you going to be able to go out there for part of the mission, or do you do all your work here in Houston?
So for the first 90 days, a lot of the science team is going to be co-located at JPL, and I will be out there for about 4 weeks of the first 90 days. After that, the science team, which goes back to their home institutions, and which is located throughout the country and even internationally. And so the rest of the mission, and the prime mission is for 2 years, will be done with the science team being remote. But those first 90 days, a lot of the science team will be out at JPL working on Mars time together.
What will you be doing while you're there?
We plan every day. We plan what the rover is going to do the next day. So you come in the morning, and your shift starts essentially right before you get data from the rover, everything that it did the day before. So you come in and you brush up on, okay, what were we supposed to have done today? And then the rover said, hey, here's what I did. You look at all that data, and then you talk as a team and say, okay, what are we going to do tomorrow? And so you spend 2 shifts over about 16 hours building a product that you're going to send to the spacecraft that tells it what to do tomorrow, and then you just repeat that for 2 years.
Because of the distance between the two planets, you've got quite a lag in communications. Does that remove any flexibility you have about what to tell your instruments or your rover to do?
No, that's right. Because of the light time delay and the complexity of the instruments, you don't really have the flexibility to make changes in real time. You plan things a day at a time. Landing is a really good example of that. So from the time that MSL hits the top of the atmosphere to the time that it lands safely on the surface of Mars is 7 minutes. Now, the light time delay between Earth and Mars right now, so the time that it takes a signal traveling at the speed of light to go from Mars to the Earth, is 14 minutes. So what that means is when we get our first indication that we've touched the top of the atmosphere here on Earth, in reality, the spacecraft has already been on the surface of Mars for 7 minutes. So really, you're kind of looking at a tape delay of events. You don't have the opportunity to respond to things in real time. And then again, the way that plays out during operations is that we do most of our communications via the orbiters around Mars right now, which only communicate with the lander a few times a day. So we have to uplink a product once a day, and we say, here's what you're going to do for every minute of this day coming up. And then it goes out and tries to do its best to follow our instructions. If we did a good job, everything will go as planned. And at the next morning when we come in, we find out how we did, and we go from there.
And found out if there were any issues that it encountered while it was trying to execute the plan.
Yes.
And do something about it the next day.
That's right.
Based on what you guys all know already and the things that your team's investigating, what are your hypotheses about the habitability of Mars?
Well, I think based on what we know right now, there's kind of some positives and negatives about possible habitability of Mars. That we have some missions that, for example, we've seen a lot of evidence for water on Mars, either in the past or even continuing up today, from the water ice that the Phoenix lander has found, or the abundant evidence of past water that the MER rovers have found, and a lot of orbital measurements that have indicated the past activity of water and possibly continuing up to present day. So that encourages you about the possibilities for life, because water is very important. It's absolutely necessary to life as we know it. But then on the other hand, the Viking mission showed us the Viking actually did carry life detection instruments with it and didn't find anything. So it shows us that the surface can also be a pretty hostile place. It's a harsh UV environment. You have ionizing radiation, chemical oxidants that can destroy life. So it can be a harsh place. But interestingly enough, it's a lot of the things that we've learned about life on Earth have informed our knowledge of the possibility for life on Mars. And life on Earth is really ubiquitous. It's anywhere you go. It's in extremely acidic or salty environments, deep undersea, deep underground in solid rock. And so right now, there's nothing about what we know about life, which has proven itself to be very adaptable, and nothing that we know about Mars that tells you that you can't have life there. You just have to know where to look, and that's the question that MSL is going to answer.
It's all very exciting. Looking forward to it. Thanks very much, Doug.
Thank you.
Dr. Doug Archer is a member of the Mars Science Laboratory Sample Analysis at Mars Science Team.